Hello again, everyone. Welcome to our discussion of section 3.5, where we will talk about complex numbers. So complex numbers is a vast area of mathematics, but in this course we will have, this is the only section where we will talk about it. And in the future, those of you who will be taking higher level mathematics, especially if there is any math majors among you, for sure you will see courses that you will have to take courses that are specifically focusing on complex numbers. Okay, such as complex analysis is one very cool course for mathematicians. Those of you who are electrical engineering or computer science majors will again take courses that have that deal with complex numbers more than other majors, and even mechanical engineers will deal with this. Okay, so before we delve into this topic, I wanted to remind everyone to please skim through the textbook section, 3.5 in this case, before you watch the video or you attend the class, and take careful notes about things that you feel are important to you as you read the textbook through that section, or write down your questions as you watch the video or read through the book. Make a note of your questions and then bring me your questions, and then review the lecture notes and solve all the problems either in the book or in my worksheets without looking at my solutions first. And then once you have your solutions already completed, then watch the video or then look at the solutions in the book and complete all the homework assignments by the due date, and then review throughout the semester. Okay, this is reviewing the previous sections as well as this section. Okay, so the complex numbers do plot on a plane like that. So this complex number has a real part. The real part is A, and an imaginary part, which is B. So how do we know B is the imaginary part? Well, it is associated with I, with this I, which we will talk about what this I represents, but it's associated with the imaginary piece of this whole number. So on a plane, the real number is plotted against what we know as the x-axis. That is the real axis. That axis becomes the real axis or real number axis. And the vertical line or the vertical or the y-axis becomes the imaginary, the axis for the imaginary part of this complex number, which would be B. So B would plot along what is known as the y-axis, which is now the imaginary axis, and A, which is the real part of this complex number, would plot against the x-axis, formerly known as the x-axis and currently known as the real number axis. So let me make it clear, because this keeps, as a matter of fact, I have it as a note here. I have it as a note and I talk about it in class, but for some reason, when I ask questions like this on an exam, a lot of people still make an error. So given this complex number A plus BI, given that, A is the real part, and I'm saying it here, A represents the real part, and B, just B, not I, the B only, represents the imaginary part. Okay, so A is the real part, and B, just B, is the imaginary part. Okay, so if somebody asks, well, as a matter of fact, I have examples here, and before we get to it, let's talk about the letter I that you saw up here. So what does the letter I represent? The I is equal to a square root of -1. How is that possible? Well, this is possible because of an agreement between all the mathematicians. So it's a definition thing. Just like the regular dictionary that defines various words, because those words we all agree mean those things, like chair, a table, and so on. This, in the mathematics world, this was defined, square root of -1 was defined as the letter I, as the imaginary, as what that letter or I represents. So if that's the case, then I squared, if you square both sides, you get -1, because this square root of -1 squared will cancel the radical expression, and we end up with just the -1. Okay? This is, I've already boxed this, but this is very, very important when we deal with this definition. Is very, very important to remember and apply when we deal with complex numbers. Okay, so now having said that, answer these questions before you see me write the answers down. In other words, please pause the video and use a pencil to answer these two questions, and then come back to the video and see how I have answered these. Okay? So I'm assuming you've done that and you already have answered these. Great. So given this complex number, the real part is 3. The imaginary part is just -8. That's what I was mentioning here, up here. A lot of people write down let me use this piece of a scratch paper, if you don't mind. A lot of people write the imaginary part as -8i. That is not correct. The -8, because it's associated with the letter I, is the imaginary piece. So the imaginary part is -8, not -8i. Okay? So this one. Again, I'm assuming you've already answered this question, which is great, and now you're here to see how I'm going to answer this. Well, if you break this up into the real part, right now the real and imaginary pieces are mixed together. We need to separate that. So, by breaking it up into different pieces, so -2/7 minus 4/7i. Right? If you break this up into pieces, you end up with that. So now it's clear what is the real part and what is the imaginary part. So the real part is -2/7. The imaginary part is -4/7. Okay? All right. So, number 3, please pause the video. Answer these questions on your own, given what we've learned in this part of the page, in these few lines, before we get to that. So remember all that, and then answer these 2 questions. Once you've done that with your pencil, come back to the video and take a look at my solution. Okay? So I'm assuming you've already done that, and you're now back with your solutions ready. Fantastic. Okay, so this plus is a neutral algebraic sign, so I'm simply going to remove it, and I'm going to write down -5 plus 5i plus 7 minus i. Okay, now we can, just like if I was an x, we can combine the like terms, right? -5 plus 7, that'll be 2. 5i minus I would be plus 4i. Okay, so that's the final answer to that. They just say carry out the operation. So what is the real part here? 2. What is the imaginary part? 4. Okay, we know that. So again, I'm assuming you've already answered this question. So the minus, I have to be careful, is not neutral like the plus algebraic sign is, right? So I need to distribute this into that and then combine it with these terms. So let me do that. -1 plus I minus 6 minus times minus positive 9I. Okay, so let's combine the like terms. Minus 1 plus 9, positive 8. I plus, well, let's see. No. What did I do? No. I have an error here, guys. Let me correct that error with my thick pen here. That's not the constant, so that's the imaginary part. So minus 1 minus 6, it is minus 7. Sorry about that. My apologies. So that's minus 7. And then I plus 9I is plus 10I. So what is the real part of this complex number? Minus 7. What is the imaginary part? 10. Okay. Okay. All right, so here we have a multiplication going on. Okay, please answer that. Pause the video, answer this, and then come back to the video for best. I'm saying this for best learning results. Okay, I'm assuming you've done that, and now you're back. So we're going to FOIL this just like we would do it with, even if we had real numbers. So 6 times 1 plus 6 times I, right? Plus 6 times I. So I just distributed the 6 into these two terms. Then plus minus 4I times 1 plus minus 4I times I. Okay? So let's simplify. 6 times 1, 6. 6 times I, 6I. Minus 4I times 1, minus 4I. Plus minus 4I times I got to be careful here because we have minus 4 here times I times I. Let's bring this back. I times I is I squared, right? I squared is I times I. It's equal to minus 1. So I times I, which is I squared, I'm going to do this in pieces so you can follow everything. So now that is equal to minus 1, right? We just know that. I is equal to the square root of negative 1. I squared equals negative 1. So let's take this one step further. We have 6 plus 6i and minus 4i add up to 2i, right? Positive 2i minus 4 times negative 1, because I squared is negative 1, equals 6 plus 2i minus 4 times minus 1, positive 4. So what do we have? We have 10 plus 2i. Okay? What is the real value of this complex number? 10. What is the imaginary part of it? 2. Okay? Okay, so the complex conjugate. Remember that when we had radical expressions like this, let me bring a piece of scratch paper here. So let me use this as a scratch paper. Remember when we had the side is better. So remember when we had, say, 1 over square root of 3 minus 2, we would have to rationalize this, right? How would we rationalize the denominator? We would multiply the numerator, or we would multiply the denominator by square root of 3 plus 2. And also, we could, to rationalize the denominator, we couldn't just multiply the denominator and then not do the same thing to the numerator, right? So we'd have to say square root of 3 plus 2 also multiplied by the numerator. So what we ended up with, we would get square root of 3 plus 2 over 3 minus 4, and then we'd get square root of 3 plus 2 over minus 1, or minus in parentheses square root of 3 plus 2. But we'd have to, this is, remember how we used to rationalize the denominator when we had the radical expressions? Remember that? We're going to have to do that here because we do not want a complex number in the denominator of a fraction. So we're going to have to multiply this by what is known as the complex conjugate. See? Complex conjugate, right there. In order to rationalize the denominator of a complex number, right? Right now we have a complex number in the denominator. We cannot have that. We want to simplify this. How? We're going to multiply the denominator and the numerator, just like what we did with the radical expressions, by the complex conjugate of the denominator. So what is a complex conjugate then? Okay, so that's what this segment explains. So suppose we have a complex number 7 plus 2i, right? Then the complex conjugate of this complex number is 7 minus 2i. So just change the middle algebraic sign to its opposite. If this was 7 minus 2i, the complex conjugate would be 7 plus 2i. Now it is 7 plus 2i, so the complex conjugate of this would be 7 minus 2i. Here, suppose we have 3 minus 5i. Then the complex conjugate of this complex number is 3 plus 5i. Okay, another example. Suppose we have 1 minus I. Then the complex conjugate of this complex number is 1 plus I. Okay? So that's the complex conjugate. And the importance of it is that we're going to use it to rationalize the denominator of a fraction that has complex numbers in it. Okay? We don't want to have, just like we didn't want to have radical expressions in the denominator of a fraction, we do not want to have a complex number in the denominator of a fraction. Okay? Okay, so now here, one of the exercises, we want to rationalize the denominator of this complex fraction so that we do not have any complex numbers like that. So the complex conjugate of the denominator here is 1 plus 3i, right? So complex conjugate of the denominator is equal to 1 plus 3i. Okay, so what do we do with that? We use to multiply the numerator and the denominator by that in order to get rid of the complex number in the denominator. So let's do that. We have, we start with 3 minus 4i divided by 1 minus 3i multiplied by 1 plus 3i divided by 1 plus 3i. So what do we get? We get, in the numerator, we get 3 minus 4i times 1 plus 3i divided by 1 minus 3i times 1 plus 3i. Okay, so now we're going to FOIL this like we did with regular numbers, right? So 3 times 1, 3 times plus 3 times so plus 3 times 3i. Okay, plus minus 4i times 1 plus minus 4i times 3i. Okay, divided by, here we need to use the special product formula. Remember that? We talked about it early in the semester. So remember, x minus y times x plus y, what we get is x, if these two terms are identical and the only difference is the sign, algebraic sign in between them, minus and plus, we get x squared, x times x squared, minus y squared, minus these two terms multiplied by each other. We can only do that if this algebraic sign is different. We could not do that with plus and plus, or minus and minus. Only if they have opposing algebraic sign in the middle with identical terms on both sides, we can do that. So this is equal to that. So let's put that property, apply that here. So that'll be 1 squared, right? These are identical terms, and the only thing different is the middle algebraic sign. So 1 squared minus 3i squared. Okay, so let's simplify. I'm going to come here. So all the way to this side. 3 times 1 is 3. 3 times 3i, 9i. Minus 4i times 1, minus 4i. Minus 4i times 3i. Minus 4 times 3 is minus 12. Right? Minus 12. I times I is negative 1. I times I is I squared, and I squared is negative 1. Remember that? I squared is negative 1. I times I is I squared. So minus 12 times negative 1. So this minus times 3, minus 4 times 3 is minus 12. I times I is I squared, which is negative 1. Okay, divided by, this is 1. 1 squared is 1, minus 3 squared is 9. I squared is negative 1. Okay, so I distributed the 2 into the denominator. 1 squared is 1, minus is minus. 3 squared is 9. I squared is negative 1. Okay, so let's simplify this a step further. So in the numerator, what do we have? We have 3. 9i minus 4i is positive 5i. Minus 12 times minus 1 is positive 12. Divided by, what do we have here? 1 minus 9 times minus 1 is minus positive 9, right? 1 plus 9, right? That gives us that. So let's simplify again. 12 plus 3 is 15, plus 5i divided by 10, right? So we've been able to rationalize the denominator. The complex number is gone. Now we have 10. Can we simplify this? Absolutely. So let's do that. So we have 5 times 3 plus I over 10, right? So this goes away, we have 1. This goes away, we have 2. So we have 3 plus I over 2. Can we simplify this? Absolutely. Let's write it down. We have 3 halves plus 1/2 I. And that's how we are able to end up with that expression. And that we've done that because it says simplify the result. We've simplified the result and write the real and imaginary parts separately. That we also did, right? If you leave it like that, the real and imaginary part are still mixed. But when you write it like this, then the real part is 3 halves, the imaginary part is 1/2, and the 2 pieces are written separately. Okay, so that's the final answer for that. Okay, so I hope for this one, if you didn't already, for the next one, please pause the video and write down your own solution, and then come back to the video and see how I worked this problem out. Okay, so I'm assuming you've done that, and now you're back. Great. So the complex conjugate of the denominator is equal to 2 plus I. Okay? 2 plus I is the complex conjugate of the denominator. We need that in order to rationalize the denominator of this complex number. Okay, so let's do that. So we have 10 plus 5I over 2 minus I, right? Multiplied by this fraction, multiplied by the complex conjugate of the denominator. So 2 plus I over 2 plus I. Okay? Then we're going to multiply 10 plus 5I times 2 plus I divided by 2 minus I times 2 plus I. Okay, so let's FOIL this. 10 times 2 10 times I, right, plus 5I times 2 plus 5I times I. So let's FOIL this. Using that special product formula, which I talked about earlier, x minus y times x plus y is x squared minus y squared, right? So we have that scenario here. So we have 2 squared minus I squared. Okay, so we're going to simplify it down here. I'm going to start on this side. So 10 times 2, 20. 10 times I plus 10I. 5I times 2 plus 10I plus 5I times I, right? That will be plus 5 times I squared, or negative 1, right? I times I is I squared I squared is equal to negative 1. So that negative 1 you see here is I times I squared is negative 1. Okay? Divided by 2 squared, 4, minus I squared is negative 1. Okay? So, let's simplify this a little more. 20, this is minus 5. 5 times minus 1 is minus 5, plus 20, that's 15. 10i plus 10i, that's 20i, divided by 4 minus minus 1, that's 4 plus 1, which is 5. Okay, can we simplify this more? Yes, absolutely, and we should, because they're asking us to simplify this as much as possible and write the real and imaginary pieces separately. So factor the numerator, 5 times 3 plus 4i, right? If you distribute excuse me, if you factoring is the opposite of the distributive property. So if you redistribute the 5 into this parentheses, you should get 15 plus 4i plus 20i. So that's how quickly you can check your own work when you're factoring these expressions. That over 5, and of course the 5 and the 5 cancel out, and we end up with just 3 plus 4i. And we don't have to do anything more because the real part is 3. The imaginary part is 4. Okay? Okay, so here, in all of these, please pause the video, write down your own solution, and then come back to the video and see what I've done. I hope you'll do that. Okay, I'm assuming you've done that and you're back to see the solution. So this one has a negative power, which we don't like, right? So the first thing we should do is rewrite this expression such that it has a positive power, or the negative power is gone. So take the reciprocal of it, you get 1 over 2 minus 3i, and that gets rid of the negative power. Now, the complex conjugate of this, let me bring this down. So the complex conjugate of the denominator is 2 plus 3i. So then we're going to multiply the numerator and the denominator of this fraction by 2 plus 3i. Okay, let's do that. Looks like I have very little space to work with here. I don't know if I can fit all the solution here. So I hope so. I hope I can. So 2 plus 3i over 2 plus 3i, right, equals 2 plus 3i times 1 is itself, right? 2 plus 3i divided by, now once again, in the denominator, we will apply this rule. If we have identical entities being multiplied with an algebraic sign in the middle being the only difference between them, we end up with x squared minus y squared. Okay? So here, we end up with 2 squared minus 3i squared. Right? Like that. Okay, so in the numerator, we have 2 plus 3i. In the denominator, we have 4 minus 3 squared is 9. I squared is negative 1, right? If you distribute this outside power into 3 and into I, you get 9 and I squared, which is not minus 1. And this minus multiplies itself by both of these. So what do we get? We get 2 plus 3I divided by 4 minus 9 times minus 1, positive 9, equals 2 plus 3I equals 13. Should we separate this? Yes, they ask us to separate this. So 2 over 13 plus 3 over 13I. And that's where we stop. Like that. Okay. Okay, so this next one is much easier than that. And again, I hope you've answered these questions and you're just watching the video to see how I'm answering, to compare your solution with this. So that is, we can rewrite this as square root of negative 1 times square root of 81. Okay, we can do that. We can separate the square root of negative 1 from that. So if I bring back, you know that we defined square root of negative 1 as I and I squared as negative 1, right? So we know square root of negative 1 is equal to I. So that is I. Okay? So that is equal to I times square root of 81 is 9, right? Times 9, or 9I. Okay, so that's the answer for that. Part H, again, let's separate these square root of negative 1 from this. So we have square root of negative 7 is square root of negative 1 times square root of 7. Square root of negative 63 can be written as square root of negative 1 times square root of 63. So we have square root of negative 1 times square root of negative 1, right? This is I. So a square root of negative 1 is I. So we have, that is I. So I times square root of 7 times another I. Now square root of 63 is square root of 7 times 9. Right? Square root of 63 can be written as square root of 7 times 9. So we can separate these, so this square root of 7 can multiply itself by that. Okay? So we can write this as, I times I is negative 1, because it's I squared, right? I times I is I squared, and I squared is equal to negative 1. So negative 1 times square root of 7 times, let's separate these two, square root of 7 times square root of 9. Okay? Now, square root of 7 times the square root of 7 is equal to 7. So we have minus 7 times square root of 9 is 3. Right? Negative 1 times square root of 7 times square root of 7 is just 7. Square root of 9 is 3. So we end up with negative 21. Like that. Okay. All right. Find all solutions of the given equation and express the final answer in the form a plus b, a plus bi. So the assumption is we know that this quadratic equation has complex roots. Okay? So let's find them. So first of all, do you see any way of factoring this? No. Because 17, no two numbers can be multiplied and give us 17 and add up to give us negative 8, right? Okay, so we're going to have to use the quadratic formula. So let me write that here. A is equal to 1. B is equal to negative 8. C is equal to 17. Okay, all right, so let's plug into the quadratic formula. Minus b is minus 8 plus or minus square root of b squared, or minus 8 squared, minus 4 times a times c, which is 17. All of that over 2a, 2 times 1. Okay. So let's simplify this. What do we get? We get x equals minus 8 is positive 8, plus or minus. That's minus 8 squared is 64, minus 4 times 17 is 68. So minus 4 times that, 68. Yes, I'll double check. I'm pretty sure it's minus 68, but why not double check, right? So right there, 4 times 17, 68. Okay, so positive 64 minus 68 will give us minus 4. So plus or minus square root of minus 4. So divided by 2, right? Okay, so that is clearly a complex number. So x equals 8 plus or minus square root of negative 1 times square root of 4 divided by 2. Then x is equal to 8 plus or minus I, square root of 4 is 2, right? Or 2i divided by 2. Okay. And then let me, because I have enough room here, let me come up here. And so like that. And then so we have, simplifying this a little more, let's factor out the 2 in the numerator. We end up with 2 times 4 plus or minus I, right, over 2. So this 2 and this 2 cancel out. We get x equals 4 plus or minus I. So you can leave the answer either like that, or you can say that the answers are x equals 4 plus I and x equals 4 minus I, like that. On an exam, this would be okay if you left it like that, but it depends on what the online homework or how the online homework management system accepts your response. So if they accept it like that, you can enter it like that. If not, you can separate the two answers and enter them separately. Okay. Usually in computer-based exams or homework management systems, they would want you to do it this way. So on a piece of paper, I'd be okay with that. But in the computer, you would probably have to do that. Okay, separating the answers. Okay, so now the next one, x squared plus 64, that's easier to solve for x, right? Simply move the 64 to the other side. that's minus 64. Then take the square root of both sides. So square root of x squared equals plus or minus, right? When we take the square root, if it's the even root we're calculating, we get plus or minus. Plus or minus of minus 64. That's clearly a complex number. On the left we have x. On the right we have plus or minus square root of negative 1 times square root of 64. And then we have x equals plus or minus I times 8, right? Square root of 64, which is 8. So let's write this in proper form. X equals plus and minus 8I. Like that. Okay. Okay. So here we have another quadratic equation. Can we factor this? I don't see it how. Because what two numbers would multiply to 10 and add up to positive 10 and add up to 6? Nothing, right? 10 and 1, they multiply to 10, but do they add up in any way to 6? 10 minus 1 is 9. 10 plus 1 is 11. So there's no way 10 and 1 can add up to 6. How about 2 and 5? Well, 2 and 5 add up to 10, multiply to 10, but can we add or subtract those two numbers in any way and get 6? No. Okay, so it's not possible to factor this. So in that case, we have to use the quadratic formula. A is equal to 1, B is equal to 6, and C is equal to 10. Okay, so using the quadratic formula, we have minus b, or minus 6, plus or minus square root of b squared, or 6 squared, minus 4 times a times c, which is 10. All of that over 2a. Okay? So if you haven't done this already, please pause the video, complete this solution, and then come back to the video. Okay, I'm assuming you've done that, which is fantastic. X equals minus 6 plus or minus. We have 36 minus 40 over 2. 2a, by the way, is 2 times 1, right? So let me correct that. That was 2 times 1. That's 1. A was 1. So which is 2. So simplifying this a little more, we get minus 6 plus or minus. This is again 36 minus 40 is minus 4, square root of minus 4, divided by 2. Right? So then we have like that. So that is, we can rewrite that as plus or minus square root of negative 1 times square root of 4. We know square root of negative 1 is equal to I. Right? We learned that on that first page. Right there, square root of negative 1 is equal to I, and I squared equals negative 1. Over 2. So let's simplify this a little more. We get minus 6 plus or minus. Square root of 4 is 2, and square root of negative 1 is I. So plus or minus 2I over 2. Okay. So now let me put the rest of this here. So what do we get? We can factor out the 2 from the numerator. We get x equals 2 times Or let's factor out, well, it makes no difference. Factor out 2, and then we get minus 3 plus or minus I divided by 2, right? Then the 2's cancel out. We get x equals minus 3 plus or minus I. So you can either keep the answer like that on a piece of paper, or you can write it separately on a computer as x equals minus 3 plus I and x equals minus 3 minus I, like that. Okay? All right. So then one last note before we close this, before we wrap up the lecture on this section. And we kind of did this. Let me bring back, we did this. This is an identity I want to speak about, but we already applied it when we were working through this part on page 3 of this worksheet, part H, square root of negative 7 times square root of negative 63. See, we couldn't say negative times negative positive. When you have a complex number, and this is clearly a complex number because you're taking the even root of a negative number, so you have a complex number, you cannot multiply the negative numbers in the roots and say positive 7 times 63, and then that is equal to positive 21. You would end up with a different answer, right, if you did that. We cannot do that, and that's what this property is saying. It's saying that a square root of negative a, or some complex number, times square root of some negative number, which is complex, is not equal to, the left side is not equal to if you were multiplying two negative numbers under the same radical expression. It's very important to remember. Okay, if you had them separate, it's different than if you had them under the same radical expression. Because, so here, we know that the left side is a complex number. Each one is a complex number, which would reduce to that. Then the left side, the right side would be, because both negatives are under the same radical expression, you could multiply them and get a positive value. You'd get square root of AB. On the left, you have i's from the complex number. So a square root of I times I is negative 1. Negative 1 times square root of AB. So the result on the left and the right are different. So just remember, when you have complex numbers separately, you cannot, in a radical expression, you cannot multiply the negatives and under the different radical expressions and say, I have a positive number. No. Only if the negative numbers are under the same radical expression, which happens a lot actually using the quadratic formula. It happens quite a lot when you end up with a negative number and then you add a larger positive number to it, and eventually you end up with a positive number, not a complex number. So if the negative numbers are under the same radical expression, you can multiply them and say they're positive. But not if the negatives are under different radical expressions. Okay? All right. With that, thank you for persisting through this video. For now, have a nice day, and I'll see you again next time.